Welcome back to Pathway to AI Proficiency. I'm thrilled to have you join us as we dive into one of the most crucial topics in machine learning and artificial intelligence, linear algebra. In our last session, we explored the different types of machine learning. Today, we're going to see how linear algebra forms the backbone of many ML algorithms. Let's get started. Linear algebra is everywhere in machine learning. From operations on arrays to data transformations and even in deep learning, understanding how to manipulate vectors and matrices is essential. But why exactly do we use linear algebra in AI? It's because these mathematical tools allow us to efficiently perform operations on large datasets and build models that can learn and make predictions. In linear algebra, understanding different types of data structures is crucial. These structures help us organize and process information effectively. Let's look at the fundamental types we use. At the most basic level, we have scalars, single numbers without direction. Next are vectors, which are arrays of scalars, providing both magnitude and direction. Matrices expand on vectors, arranging numbers in a two-dimensional grid, allowing for complex operations and transformations. Then, we have tensors, which are like high-dimensional matrices, used extensively in fields requiring multi-dimensional data. Identity matrices, with ones on the diagonal and zeros elsewhere, are pivotal in matrix operations. Diagonal matrices have non-zero elements only along the diagonal, simplifying many matrix computations. Sparse matrices are primarily made up of zeros, used when data is minimal to save space and improve efficiency. Finally, symmetric matrices are equal to their transpose and are key in many applications due to their balanced properties. Each of these structures plays a specific role in mathematical computations and has unique applications in machine learning and beyond. Understanding these will help you grasp more complex algorithms and techniques used in artificial intelligence. Let's delve deeper into scalars, the simplest type of data structure in linear algebra. A scalar is a single number, typically used to measure magnitude or scale quantities. Unlike vectors and matrices, scalars do not have direction. Any single numerical value like 12, minus 4.65 or 7 are considered scalars. In everyday math, when you multiply a number by 2, you are scaling that number by a scalar of 2. In physics, speed can be considered a scalar, where it gives magnitude but no direction. Now, let's explore vectors, which are fundamental components in fields ranging from physics to machine learning. A vector is an entity that has both magnitude and direction, making it more complex than a scalar. Unlike scalars, vectors are directional and can be represented in n-dimensional space as an ordered list of numbers. Each number represents a component in a particular dimension. Mathematically, we can represent a vector as a column or row in a matrix. For example, the below represent vectors in three-dimensional space. Before we dive into the Python code for manipulating vectors, let's briefly talk about NumPy. NumPy, which stands for Numerical Python, is one of the most essential libraries used in the Python programming language, especially for data science and machine learning. NumPy provides support for large, multi-dimensional arrays and matrices, along with a collection of mathematical functions to operate on these arrays efficiently. The reason it's so valuable is that NumPy is designed to handle large datasets with high performance and ease of use. In the context of linear algebra, NumPy is particularly useful because it offers functionalities like matrix multiplication, transposition, and other operations critical in data analysis and machine learning. It allows us to perform calculations on vectors and matrices with simple, concise code. Using NumPy simplifies complex mathematical operations and makes Python code more readable and efficient. Its ability to perform operations in vectorized form speeds up calculations significantly compared to standard Python loops. Let's see how NumPy can be used to perform operations on vectors. We'll create vectors, perform additions, scalings, and more, demonstrating the power and simplicity of NumPy in handling mathematical computations. With this understanding of NumPy, we're now well prepared to look at some practical examples of vector operations using this powerful tool. In this segment, we'll explore how to perform basic vector operations using NumPy, a powerful library optimized for numerical operations in Python. First, we need to import NumPy and define our vectors. We start by importing the NumPy library with import NumPy as np. This allows us to use functions and methods available in NumPy. Then, we define two vectors, vector underscore a and vector underscore b. Here, vector underscore a is an array with elements 2, 3, and 4, and vector underscore b is an array with elements 1, 0, and -1. Imagine vector underscore a as an arrow stretching from the origin in a three-dimensional space, pointing towards the coordinates 2, 3, 4, and vector underscore b pointing towards 1, 0, -1. To add these two vectors, we use the NumPy function np.add. Adding vector underscore a and vector underscore b element-wise gives us a new vector where each element is the sum of the corresponding elements in vector underscore a and vector underscore b. The result is added underscore vector, which would graphically be the diagonal of the parallelogram formed by vector underscore a and vector underscore b. Next, we perform scalar multiplication. Multiplying vector underscore a by 2 scales each component of the vector by 2. This operation stretches vector underscore a to twice its original length in the same direction, resulting in scaled underscore vector. When we print these vectors, vector a shows the original coordinates of vector underscore a, vector b for vector underscore b, added vector for the result of our addition, and scaled vector shows the result of the scalar multiplication. This output helps verify our calculations and understand the changes visually. Using NumPy to handle vectors simplifies these operations significantly, making it a favored tool in scientific computing and data analysis. By using NumPy's array functionality, we can perform complex vector operations with just a few lines of intuitive code. Now let's explore two fundamental forms of vector representation used in linear algebra: column vectors and row vectors. Understanding the difference between these is crucial for performing matrix operations and data transformations. Column vectors. A column vector is a matrix with a single column but multiple rows. It represents vectors vertically, which is a common format in mathematical and machine learning models due to its alignment with matrix multiplication rules. Row vectors. Conversely, a row vector has a single row but multiple columns. This horizontal format is also used in mathematical computations, especially in scenarios involving row operations or system states. Python implementation. Using NumPy, a versatile library for numerical computing, we can easily create and manipulate these vector types. Let's see how these vectors appear in code and output.
Explanation of code and graph. 1 matplotlibs matshow. This function is used to visualize the column and row vectors. It creates a heat map-like visualization for the arrays, making it clear how the data is structured in each format. 2 visual distinctions. The column vector is displayed vertically, emphasizing its structure, while the row vector is displayed horizontally. 3 titles and labels. Each subplot is clearly labeled with titles and tick labels that match the vector elements, enhancing readability and understanding. As demonstrated, column vectors and row vectors are pivotal in defining data structures for computational mathematics and machine learning. Their representation in NumPy is straightforward, allowing us to focus on higher-level computations and applications. Thank you for joining me today as we explored the foundational concepts of scalars and vectors. These elements are crucial in the world of mathematics and computational sciences. But our journey doesn't stop here. Tease the importance of matrices. In our next video, we'll dive deep into the world of matrices. Matrices are not just arrays of numbers. They are powerful tools that form the backbone of many machine learning algorithms and are integral to the operation of neural networks. We'll explore how matrices are used to represent and manipulate data, how they are crucial in the training of neural networks, and their role in transformations and state transitions in complex systems. Engagement and educational goals. Whether you're a student trying to grasp the fundamentals, a professional looking to refresh your knowledge, or simply curious about how machine learning technologies work behind the scenes, our next episode will provide you with the insights you need to understand these complex concepts. So make sure to subscribe and hit the bell icon to not miss out on our deep dive into matrices. You'll learn not only about their theoretical aspects but also see practical examples of how they drive modern technology in fields like artificial intelligence and data science. Thank you for watching, and I look forward to unraveling the mysteries of matrices with you in our next video. Stay curious and keep learning.